Hello again. We tried to show you some of the other examples, which we solved one of the questions in the class, but now we go and add more things to this question. So you have already created a script that plots experimental buckling data, the text file, which we did read. Now, the objectives of this exercise is to calculate the theoretical critical load given a specific column length. Like we will need to plot this theoretical point on the same plot on top of the experimental data. But we have the following specifications for that, which is the materials. It's made of a steel, 200 gigapascal, sorry, and the stress 250 megapascal, and the diameter is 12 millimeters. We assume the column is fixed at both ends, and then we need to find how we can investigate this using the buckling theory or the equations for it. So if you go to resources, you find the formula sheet. I'll share this formula sheet with you. So you find this is the formula sheet we use in strength materials exam. And if you go to the second page, you find the topic buckling. And in that topic, we need to calculate the cylinderness ratio, which is equals to the equivalent length divided by the radius of gyration, and then the cylinderness ratio limit, which is calculated based on that equation. And the equivalent length, you have 4 scenarios: pinned both ends, or fix both ends, or pin one end, fix other end, or fix one end and free the other end. So in our case, as stated in the question, the column is fixed at both ends, so it would be 0.5 the length, that equation for the equivalent length. And then we have 3 equations to use, either the earlier method for calculating critical, Rankin-Gordon or Johnson, and then we embed this equation. But remember here, there is a constant here represent A. A is the relation between the yield stress and pi square divided by Young's modulus, which is given. So that's why we call it a constant, because this is given in the question, but the rest, it's required to calculate the following parameters like A, and the area, and the cylinderness ratio. And we go through it. So these equations, technically, we'll embed them in the script, and we try to find out. Okay, we go back to the MATLAB script. First of all, I need to, again, CLC, clear, and then close all. That's to make sure, like, if I had the previous script, will not impact on my current script. Now we call it experimental buckling data. So we're trying to read the text file, which I'll show you. You can use the command CSV read, and then we need to really just copy that F2, Control A, the text file, which I will open it for you and to show you some information. Make sure to put that to make sure that we're following the text file or reading the text file. So if I click on the buckling file, you can see it here will open for us. It's giving us the length and the critical load, and that's what we're trying to determine here. And since I don't want the text to be impacted on me, I can delete that line, the first one, and bring this up and then close. It will ask me to, yes, do you want to save that? So save it. So when I run this script, you can see first I need to save it. So I will call it buckling example. All right, now you can see already upload. I brought those this text file to X and Y, or 2 columns to represent the information we're trying to determine. All right, so let's start to bring our inputs. So we have the diameter. It's given to us 12 millimeters, so units, millimeters, as stated in the question on the top. I'll put this on side so people can see the comments easily. And also is giving to us E, which is stands for Young modulus. Again, I work 200 E3 because megapascal and millimeters, they work nicely with the conversion, so will not impact to me. And we can see that in SolidWorks as well. I will show you that when we start with the FEA analysis of SolidWorks. So that will come again here. And then what we have the other information given to us is the yield stress, 250 megapascal. So I will write that underscore stress. Avoid gaps and spaces and just write it in the way like we're learning in the class. 250. I'll put the semicolon because I don't want to show this results, and I put the units for that. It's megapascal, as you can see it in the question. I forgot to put the semicolon here, so I will add them to make sure will not impact on my answers. Awesome. So these were the 1, 2, 3 inputs given to us in the question, and now we try to find the formula. So other things which we say we could write in the script, I'll show you, which I say it is a constant. So if I go to the screen and again and share with you, this A value is actually a constant, is a relationship between the yield stress, which is 250 given to us, and pi square divided by E Young's modulus. So I can technically calculate this without involving even the questions. So I could call that A. And remember, the close all will close all the figures, close everything. So if I use the A in previous examples, will not interfere with my application. So I will copy again this one, yield stress. Again, if I misspelled the yield stress by any mistakes, so I will need to copy and continue with that mistake, or later we can always fix it. Pi to the power square divided by the E, which is given in the question, and then we put it on the side. So that is considered for us the constant. That what we call it, we could define it as a factor in Rankin-Gordon equation, which I needed later. Okay, so that's if it's in case you're wondering where the A comes from, that is from the formula which I needed later if I want to perform the calculation for Rankin-Gordon for it. All right, now we need to use the column length. So I'll start with a value of 350, the column length in this question. So I'll write column underscore in length equals 350. And remember, this is in millimeters, 350. So I'll write units in millimeters. I choose a value which it can easily find in the text file. So when you come to experimental data, you can see the 350 is already exists here, which is giving you the load of 20,658. You can select any values of this, but we're comparing entire experimental data to one point, which we calculated, we'll be calculating based on the theories. All right, so now we need to find the effective length, or LE. So I'll call it LE at this stage. And LE equals, for this case, is 0.5 times the column length, because that effective length will be, I'll write the comments here. So we call it effective length for us. And that is also, it's fixed at both ends as stated in the question. So you can see here, assume the column is fixed at both ends. And based on the formula sheet, we can see that the value for it is 0.5 L. Whatever is the length, 350 millimeters, and that will be 0.5 for that value. Okay. just tidying up things. You can always tidy up the script every time you go, and you edit, you see some errors and mistakes, make it looks better. Okay, now to start with this, we need to technically calculate the slenderness ratio with respect to the radius of gyration and comparing it to the limit, and then based on that we can select the one of the three methods. We're writing an if statement for it. So to calculate that, we need to find the relationship between them. So there is always an equation. I'll show you now in the formula sheet. I'm just switching to the formula sheet. So you can see there's a relationship between them. I represent the second moment of area, A is the area, and K is the radius of gyration. So technically, to calculate K value, I need to take the root square of I over A, and then that will give me the value for it. So go back to my script and reorganize that. This is all available with the formula sheet. So I'm now back to the script, and then we'll define these values. So first of all, we start with the second moment of area for a circular shape. It's pi d to the power 4 divided by 64 for a circular shape. So that we call it second moment of area in millimeter to the power 4, because that's how it's calculated. So its stick would take the diameter, which was assumed 12 millimeters, and based on that, will calculate for me the I. Now, the second things, we need to determine the area. The area is for a circular shape, so either pi r square or d, because we have a d. So pi is the first constant, will be recognized, times d square divided that value by 4. And remember, MATLAB use BirdMath, so we start the BirdMath application, and that will be the area we're trying to calculate, area in millimeters square. We're doing millimeters square because remember the diameter is in millimeters. And here is always, that's why I say the comments will be nice for everyone to see that. Now, if I missed that, I could just update the script. And technically, every time I like really to run the script to make sure it's working, no issues, and I see the calculations is already performed there. To calculate for me the constant A, the area, the column length is 350, we selected. We can change these values. We can even put a statement into the length, similar input value, and you put between brackets into the length, the column length, and then based on it, perform for you the calculations. And you can even give a comment for that or restrictions for it. All right. So now we could calculate the radius of gyration, K equals square root. Is that how we write it? Square root for it will be I divided by area. Make sure it spells the same way. And that will calculate for us the radius of gyration. And in the units for it is millimeters, because it's radius. All right. So now we need to find the limited slenderness ratio. So I could say limiting slenderness ratio. So I could say SR to make it easy equals. So based on the formula given to us for slenderness ratio under buckling, you can go and check it out later. It's the square root 2 pi square E over the yield stress. So everything is available on it. It means we have a constant, so we can write the equation square root brackets 2 times pi square times E, which is Young modulus, all of that divided by the yield stress. And as I say, because I can easily copy this, if in case I misspell something, will come with exactly the same way. So that is, we call it, we write a comment, the limit of the slenderness ratio. So that is the one. Based on it, we need to write an if statement to make sure mine will be either working with it. So cylinderness ratio, SR, is equals cylinderness ratio based on the equation is LE over K. So LE is the equivalent length divided by K is the radius gyration, and make sure if I spell it capital or small letter it should be the same. So that one we call it cylinderness ratio. I know it should be as a comment, and that's why you make sure, like, whatever things you can organize it nicely. Okay, so now I have the limit. I can run the script and see what it will show me. So I got the limiting cylinderness ratio, which is 125.663, and the cylinderness ratio is 58 for that example. So definitely I am below the limit for it, and therefore I need to write my if statement for that. So if yield stress, so yield stress is less or equal than critical load equals yield stress should be equal, less or equal, yield stress times the area. Else if but that one should be the cylinderness ratio for it. So instead of yield stress, we could say cylinderness ratio, SR, because it's not the yield, it's less or equal 10, then the critical load equals the yield stress multiplied. So where is the yield stress? Multiplied by the area critical load. That's the cylinder ratio is equals. Else if here would be cylinderness ratio, SR, is bigger than 10, and another statement. So we have so bigger than 10 and SR is smaller or equal the limit, which is the limiting SR ratio. Then what we have, critical load, we'll use the method, equals to what? Equals to yield stress again times area divided by, we'll use the ranking order method, 1 plus A times cylinderness ratio, SR, all of that will be square to the power 2 or square. All right. Else, the final option would be for that. Critical load equals, the last method is the, which we're trying to use, it's pi square times E times area divided by the cylinderness ratio, which is SR square. So that is cylinderness ratio, and you go through it. That statement to finish, we call it end of that statement, if a statement. And then after that, we start figure to plot the relationship between them. I will just with this figure. And then from the figure, we could plot. We have the column length, first one. And then that will represent the x-axis, and critical load, it's the y-axis. And we could choose a color, for example, BO. And then hold on to add to the graph, plot. We bring now, what we'll bring experimental buckling, but we need to make sure we, as we say in the class, to bring the data for X and Y, and experimental buckling again for the second column, and that we could give it a color red X. We finish from that, we could add legend, and that legend will be called, the first one is theoretical, critical load, versus the second one, experimental data. So that is the legend for the two data we have. X label. So what we'll label in the X, you have the column length, and that units is in millimeters. And the Y label, the Y will represent for us critical load. In newtons. And then we have we could add the title with that, theoretical. So the title, we can actually just copy the legend with some modifications. That's the easy way. So you can just put that verse and bring this one here that way. And then we can add a grid on. Sometimes you can put hold on and hold off here if you need it, but sometimes we don't need that. And then we can run the script and see if it's working. All right, so it's working. So basically what we're trying to achieve here to compare our theoretical, which is calculated based on this point. You can see when I put the mouse here, is the 350, and the Y value is about 19,758.9 or 19,758.9 newtons, the critical load for it, compared to the experimental data we're going through it. So that is the critical load for what we're trying to achieve for plotting between stress. So the question here, it's very important. You set up the equation with showing all the values, like the diameter, E. I could even change the value for the length again, like I could put something instead of column 300s, we put 400, for example, and save, and then run it again. And you can see it's now shifted the point to 400 and giving me different critical load for it. So the script is working nicely with no problems. All the comments here. Here is where it's the interesting thing. So you have the cylinderness ratio, you compare it to the limit. So if cylinderness ratio, it's less or equal than 10 based on the theories of buckling, then you straightforward use the equation critical loads is equal yield stress times the area. Now, if the cylinderness ratio is bigger than 10, or cylinder ratio is less or equal the limiting, remember the limiting as we calculated here, you can see limiting is 125, then it should go and calculate the critical load using. So I could really just put this would be Rankin Gordon theory, and all you could even add the other theory, which is Johnson, if you want to use the other one. So either use the critical. Now, if the critical, if the other option that is not within this, then you can use the critical load to be your Euler method. So you can use this one as the last option for it. So it depends on what is actually you're trying to calculate here and the theories you're trying to use. So that was the three if statements. So this script to go and show you if statement. Now, why we use figure and plot on, hold on and hold out? Because we want to make sure we can add the experimental data, the one we read from here. And remember, we use the 1 and 2 for reading the this first column and second column, and then we go through the rest of the data to show them nicely from the text file. So in red is the experimental, the blue is representing my theoretical one calculated from the script. So it's a very simple script, but it's showing a lot how can we plot and present the result nicely, an easy script so people can follow. I hope you enjoy this video, and please, if you have another way to improve it or something I've done wrong, let me know. Thank you very much.